So today I want to continue along the lines of discussing synchronization, which is what we were doing last time. And this slide here is attempting to basically remind you of exactly what the issue was. So we're in a threaded domain where we have multiple threads running at the same time. And this was this example from the bank account where we're trying to do, in this case, add some amount to our balance. We grab the account value, we add the amount to the balance, we store it back. And this looks all fine and dandy until you have multiple threads going on, and then poof, we have this scenario where we could have two threads that just happen to be doing deposit at exactly the same time, and because things end up being interleaved, you get behavior you didn't expect. So that in this particular interleaving, one of the deposits go away. Okay? And actually, in most of the interleavings, you're going to end up losing one of the deposits. The only ones that work well is if all three of the instructions happen before or after the other three. Okay? Now, we talked about this notion of an atomic operation, which is an operation that always runs to completion or not at all. And for this particular example, what we'd really like is we'd like to be able to tie these three instructions together as an atomic operation. If we could somehow do that, then there'd only be two possible ways that could go. Either the first deposit goes first or second, and there's no kind of confusion as to what the state is when you're done. Here was our first attempt to actually get atomic sections here, or atomic operations, critical sections, and as you notice, it ends up being pretty complicated. So what were our assumptions here? Our assumptions were basically that we only have loads and stores that are atomic. We do not have any extra operations. And as a result, we had to go through this kind of complicated process of designing something which basically had two notes, and one of them, thread A, actually did a little extra spinning than thread B. And when we were done, we pseudo-convinced ourselves that this works, right? And the important part here is this if no milk, buy milk, which is on both sides. That's the critical section we're really trying to protect, or that's the atomic operation in this case. Checking for milk, buying milk is together atomically, and it's when we interleave the two in some weird way that we end up with that scenario of too much milk. Okay? Are we good on this? Did anybody stare at this and convince themselves it doesn't work? Come on, somebody must have convinced himself it doesn't work. No? All right. So I will mention a little later that I've already convinced you this works. It turns out that if this is a multiprocessor and you've got two threads that are running on different cores, it's possible that this still won't work. Depends on whether your memory model is sequentially consistent or not. So you don't have to worry about that, but that's yet another strike against this particular obscure code. So what we'd really like to do is we'd like to do better. And that's what this lecture is going to be about. Is there a better way? And so the critical section we're protecting here is the if no milk, buy milk. It's really complicated. And the other part is that A actually has something in the middle here. I pointed it out before, but let's look at it explicitly. If A is misfortunate enough to leave a note right around when B left a note, then it's actually got to sit here and spin, possibly while B goes off to the store. Okay? So, this is going to be one pissed off roommate, right? They can't even decide whether to go to the store until the note goes away. Okay, so that's called busy waiting, and it turns out that that's actually bad, as you can obviously see from the roommate analogy. It's also bad from a CPU analogy, and the way to think about that is A is busy waiting for B to do something, but A's got the CPU. So B isn't even running, right? So A is just busy wasting time, and B can't run. So you know that A is going to waste all of the time until the scheduler or the timer comes by, switches it out, and pulls B in. Then B can resolve the situation. So this is called busy waiting, and it's in fact something that we are going to so strongly discourage, we're going to give you a very hard time about it on exams and stuff if you happen to do it. Now, there's a better way. The better way is to have actual hardware primitives that we design that are set up for synchronization. So it's more than just load and store being atomic. Okay? And then, of course, we're going to even build higher level primitives out of that. So the goals for today are hardware support for synchronization we're going to talk about. We're going to start talking about some of these higher level primitives. We're certainly going to talk about semaphores and locks. We will mostly start on monitors, but if you come to a section on Friday, they'll definitely talk about monitors. And on Monday, we'll give you the readers-writers example as well. If you're anxious to learn more about monitors before Friday or Monday, you could always go to last fall when I taught this and play the video for yourself too, I suppose, for that lecture 8, if you really wanted to see it. Okay. And we're also going to touch on programming paradigms for concurrent programs. Now, this is a frame from my favorite Dilbert cartoon of all time. I used to have this up on my door where they're going around the table, and the boss says, well, why don't you tell me, that's the pointy hair guy, he says to this guy, why don't you tell me about your project? And he says, my project's a whole new paradigm. And then people are like, paradigm, what's that? Well, you know, paradigmism, as in my project's a whole new paradigm, but enough about mine. What about yours? And then, of course, they all go around, mine's a paradigm, mine's a paradigm. So we're actually, paradigm means pattern. We're actually going to talk about some patterns, okay? Maybe not whole new paradigms, because these have been around for a while, but certainly some paradigms. So the high-level picture here is that the abstractions of threads are useful. It gives you this sequential execution model where you can say, well, I'm going to do a bank account deposit by first grabbing the account and then doing the addition to the deposit and then storing it back. And you as a programmer can think as a single thread. And it's up to the OS to multiplex these so multiple threads are running at once, and you don't have to worry about that, fortunately. Unfortunately, what you do have to worry about is now you have to make sure that if two threads are interleaving in a funny way, it doesn't screw up your data. Okay, and that's where the synchronization comes into play. So threads are good to think about for parallelism, but they introduce the need for synchronization. And you know, basically what it boils down to is anytime you have shared state between two threads, they can screw each other up, and you've got to somehow deal with that. So we're going to build you a toolbox, a synchronization toolbox, if you will, and explore some paradigms. Okay, and so we're going to start with lock idea, and this was solution number 4, which we gave you at the very end, which is suppose we have a lock. Now, we don't know how to make a lock, but the idea here is there's a lock.acquire operation, which basically says wait until the lock is free and then grab the lock. Now, notice the term wait in here. Okay, I don't know if you remember, but last time I said every synchronization operation potentially involves waiting. That's how we avoid screwing things up. Remember that interleaving I showed you at the bank? We sort of had one instruction and then two, and things got in between there. The way we fix it is we wait. We force these 3 to wait until we're done with the other 3. Okay? Just because we say wait doesn't mean busy wait. So what we ideally would have is if you end up waiting because the lock is busy, you'd really like that the thread that's waiting to be put on a wait queue and not be taking CPU time. Okay? That's how we're going to distinguish there. Now, lock.release is something that should only be run by the person who has the lock. And lock.release says, OK, I'm now freeing the lock up, and you could wake up somebody who happens to be waiting on the lock. Okay? And these are atomic operations. So however lock.acquire is produced, and we'll talk about several implementations in a little bit, it should not be the case that two lock.acquires can interleave somehow. Okay? Whatever lock.acquire is, it ought to look atomic from the standpoint of the people using it. Okay? Because otherwise, what's the point? Right? It ought to be the case that when you execute lock.acquire, you really do wait until lock is free and then get the lock. Okay, any questions so far on that? Okay, so this makes our milk problem really easy. The thread does milk lock.acquire, if no milk by milk, milk lock.release. Okay, very easy. And the other nice thing about this solution is we could do this with 100 threads. Okay, so this works in a fraternity. Okay, I don't know how many people they shove into a fraternity these days, but and The other nice thing is the roommates who are busy waiting to look in the fridge are sleeping, so they're maybe on their feet sleeping, but at least they're not busy waiting, so they're not getting pissed off, right? Okay. Now the section in here, again, is going to be called our critical section, and this is the section of code that we're protecting, and basically the semantics are exactly one thread can be inside the critical section at once, and that's what we're doing with the locks. Okay? All right, and we can always buy ice cream instead. But are there any questions on the lock paradigm here? I still haven't showed you how to make one yet, but suppose that I could. So does this make sense to everybody? Yeah. Yeah, so the question is, if thread A acquires the lock and thread B goes to try to acquire the lock, yes, indeed, thread B is put on a wait queue associated with the lock. Now, by the way, notice how I've given this syntax here, milk lock.acquire. The implication here is that I could have an arbitrarily large number of individual locks in the system. Okay, and I'm just, and each one of them could protect something different. Okay, any other questions? All right. So how do we build them? So the lock is preventing somebody from doing something. Okay, so we're locking before the critical section and unlocking when leaving and waiting if locked. And again, the point is that all synchronization involves waiting somehow. Now, if you look at the load store solution from last time, milk number 3, it's pretty complex, it's error prone, and it's not really the way we'd want to do a lock. And it also has busy waiting in the middle. So suppose that instead of trying to do what we did with milk solution number 3, we build a hardware lock instruction into the hardware. So we're producing the newest version of the x86 processor, and we build a lock and an unlock instruction, and we implement them in silicon. Now, is this a good idea or a bad idea? It's certainly atomic. I'm assuming that the instruction can't be interrupted, so that atomicity thing is there. But is this a good idea in general? Go for it, yeah.
No, because then you could only have a limited number of blocks. Because I don't see how you could have it, how to just lock a specific part of code.
So your worry here is that if it's a hardware instruction, we're forced to have a limited number of locks. Now, I would suggest that perhaps we could actually give a DRAM address somehow, and then maybe that wouldn't be a limitation. What else? Yeah.
Couldn't something just grab the lock and then sit there forever?
So you're worried about bugs. So here the question was, couldn't somebody grab the lock and never release it? Certainly. That will be the very first deadlock you all code, I'm sure. Yes. So you like the hardware idea because it's potentially more optimized for the scheduling of threads. Okay? Yes?
I'm worried that every time you want any kind of high-level software construct, you're going to try to create hardware.
Okay, so you're a hardware skeptic, which is good. I don't know if I told you this at the beginning of one of my first lectures, but I always like to joke about the VAX because by the end of Digital Equipment Corporation, they had their polynomial multiply instruction. So I'm with you on that somewhat discomfort. But there's actually a very good other argument against this. Yes?
What if the hardware, what if the that you get the user-level software uses the hardware lock and causes a deadlock because that program?
Okay, so you want to make sure that even if a user uses a lock, that it won't lock the system up. Okay? That's a good concern. Yes? Yeah, but I'll grant that the compiler might be able to deal with it. But you're right, more complexity, yeah, in the back.
Well, I mean, it depends somewhat on how you implement it, but you want the operating system to be able to put the person that's acquiring the lock off the processor.
Ah, there's the rub. Right there. The problem here is, remember how I said that when you try to grab the lock and fail, you want to be put on a wait queue. If we do a hardware lock instruction, now suddenly we're coding parts of the operating system into the hardware because we've got to figure out what our wait queue structure looks like. All right, so that's actually a serious downside to having a hardware-only lock implementation. Yes?
Why wouldn't you
possibly. So you're saying some sort, well, that would be much more like a system call than a hardware lock instruction, though. Okay.
Couldn't you
So,
still have a hardware lock that just test and set a bit and then read back whether you got it set?
but see, now you're splitting, so we'll actually do that in a moment. Now you're splitting the check for the lock versus the what to do when you fail. So that's good. Let's hold that thought because we'll get there in a couple of slides. So basically, that's basically this issue of putting things to sleep is challenging, and you end up with serious complexity. There actually was something in the Intel 432, and I guarantee none of you have ever run any code on an Intel 432. If you have, I'll be very surprised. I think they produced some sample chips and abandoned the product before it ever got very far. And this was because they did all sorts of stuff. I mean, they had tag bits, they had Huffman encoded instruction links. This was pretty cool. So that your code was the smallest possible size and so on and so forth. All right, so we're not going to do it fully in hardware. Now let's do something a little different. Let's consider interrupt enable and disable. Can we build multi-instruction atomic operations with interrupt, disable, and enable? How many people think that seems plausible? Okay. The trick, so I'll agree with that. Now the trick though is, why is it plausible? Okay, and you have to think that through. What I'm doing by disabling interrupts is I'm actually preventing the timer from going off and stealing my thread out from under me, stealing the CPU out from under me. So by disabling interrupts, what I'm really doing is preventing the scheduler from switching. Okay? Now that's all fine because that gets rid of the external switching we've been talking about. But if the thread disables interrupts and then tries to do I/O or does something else we've been yield that we've been typically calling an internal event, you've just really screwed your system up. Okay, so you can't disable interrupts and then go off and do something that relinquishes the CPU. Okay, you got to be very careful about that. So we've got to be a little careful. And on a uniprocessor, disabling interrupts basically allows us to prevent the external things, and as long as we avoid the internal events, we're okay. What about a multiprocessor? If we have more than one core in the system and we disable interrupts on one core, does that prevent the other core from going in there and messing us up? So it doesn't, because you're only disabling interrupts on one particular core. So you got to be either disabling interrupts for the whole system, which now it's like, ooh, that sounds bad. Disabling interrupts for a short period of time on one system is one thing, but disabling for the whole system seems bad. Or if you disable interrupts on only one core, you're confused that that's a good thing. Okay, so you got to be very careful. Yeah. Yes, so you could potentially still have a problem if you have hyperthreading as well. And hyperthreading is very close to having two processors in the way it works. Yes. Okay, so you got to keep that as a caveat. Disabling interrupts has limited use. You have to be very careful that you're not competing with other CPUs or even other hardware threads as in a hyperthreaded scenario. So here is a lock, acquire, and release implementation. Lock, acquire is disable interrupts. Lock, release is enable interrupts. Good, bad, indifferent. What do you think? So caveats, we only have one CPU. It's not hyper-threaded. We're not going to be dumb and do internal event yields. Does this work as a lock, acquire, and release? How many people think it works? Okay, it works, but how many people think it doesn't work? Okay, how many people are not sure? Okay, so it works. Okay, this is a working lock, acquire, and release, and unfortunately it's not a very good one. Okay, and problems are the following. You certainly can never let the user do this. Okay, user code, lock, acquire, while true. Okay? Now you've just toasted your system. Why is that? Well, interrupts will never go off again. The OS will never grab the CPU back. and basically you're busy computing 0 or something. Real-time systems also very bad, right? Because since we've locked out timers and stuff, any real-time events that we might be hoping to get are suddenly toasted by this approach. Because if we do a lock acquire and then have a huge critical section before we do lock release, then all bets are off as to timing. Okay, now maybe you have a system that you don't care whether it's responsive or not, but usually when you have a system that's not responsive, the first thing you do is reboot, right? So what happens with I/O? Reactor meltdown about to happen. Oops, interrupts are disabled. I guess I'll ignore it, right? So basically, locking out interrupts is also bad from an I/O standpoint. And in reality, hopefully, you're not controlling a nuclear reactor with user code that can disable interrupts. But in reality, you might have packets coming in off the network and a queue overflows, or you might have the disk drive returning and you lose some data. So it actually isn't so good to disable interrupts for a long period of time. Okay? Questions? Yeah.
What about non-maskable interrupts? How does that play into lock acquire?
So non-maskable interrupts can't be masked, so you can't disable them. And so basically, you don't want to do anything that's going to compete with the non-maskable interrupt handler because there's no way you can prevent it from coming in. Good. So let's do a better implementation, okay? So the key idea here is we're going to maintain a lock variable in memory, and we're only going to use interrupts to maintain mutual exclusion on the lock variable. Okay, so here's the idea. The lock itself is just going to be an integer, or a bit, actually, is all it really needs to be in memory, which we're going to initially set as free. Okay? And here's what acquire looks like. Acquire disables interrupts, says if the value is busy, put the thread on the wait queue, go to sleep. Otherwise, it sets the value to be busy and exits. Okay? Now, hopefully, this path between disabling and enabling is fairly fast. Okay, so we don't actually disable interrupts for very long. Now let's take a look at what release looks like. So release disables interrupts, says if anybody's on the wait queue, take a thread off the wait queue, put it on the ready queue. Otherwise, set the value to free and exit. Now, let's see if we can figure this out. So clearly, if nobody's using the lock, then the acquire is easy. Everybody see that? You disable interrupts, you check it. You fall through here, you set the value to busy, you re-enable. So that one's not the hard case, okay? And of course, with release, if there's only one thing in the system, you disable interrupts, nobody's on the wait queue, set the value to free, enable, and go. So hopefully, you guys can see that one thread here is easy to think about. All in favor, say aye. That one's easy? Okay. It's the two-thread case, or the n-thread case, it's a little trickier. Let's take a look at that. If we've already got one that has set value to busy, let's see what happens. The next guy comes along, tries to acquire, disables interrupts, says, is the value busy? Yes. Puts the thread to sleep, puts the thread on the wait queue, and goes to sleep. Okay. Now, what happens later when somebody goes to release? Well, what happens is they say, is anybody in the wait queue? Well, yes, they are. They were put on over here. Take them off the wait queue, put them on the ready queue, at which point they'll wake up and fall through here. And of course, notice that in this arm here, we didn't actually set value to free again. So we're going to keep the lock taken. And so this guy will basically just fall through and run. OK, stare at that for a little bit. Now, there's a subtle little problem in the middle here that I'm sure somebody's going to catch. Yeah. Okay, so you're worried that the one that just got woken up re-enables interrupts. Okay. Yeah, so there's something funny with something. I pulled a fast one on you with interrupts here, right? There's something goofy. Let me give you an even worse example here. I disable interrupts and I go to sleep. Okay? That sounds bad. Because who's going to re-enable interrupts? Right? And more interesting even than that is, suppose I try to enable interrupts in here. Where do I do it, right? Because I can't really enable before I go to sleep, because then somebody could, try to wake me up before I actually go to sleep, and there's something funny with interrupts in here. So I think this is as a solution, this guy's kind of a B+. Okay, it's sort of there, but it doesn't really work. Okay, so let's talk about this interrupt for a moment. So why do we need to disable the interrupts at all? And the reason is that the way we're doing this, we have to make sure we avoid interruption between checking to see whether the lock is taken and grabbing it. Because if we check and we say, oh, look, the lock is free, and then we go to grab the lock, and in the meantime, somebody else grabbed the lock, now we've got a problem. Remember how I said acquire has to be atomic? Well, here's acquire, and the way we make acquire atomic is we disable interrupts and re-enable it so that this thing in the middle here is truly a critical section that only one thread can ever be in at once. Okay? So the disabling and enabling of interrupts are really required to avoid having two people have the lock at once. Okay? And treat this as a critical section. All right? Now, one thing that's good is ignoring this whole go to sleep thing, which is a little longer. We've basically made sure that between disable and enable, we have a very short period of time in here. Okay? So now I'm seeing some confused looks. So you have to sort of separate the implementation of the lock from the use of the lock. So if you have some code that acquires the lock and goes and computes 1,000,000 digits of pi and then releases the lock, that's okay here because we only disable and enable interrupts just during the period of acquiring and releasing the lock, not during this critical section which the user program's using. Okay, so you've got to distinguish the implementation of the lock from the use of the lock. Is everybody with me on that? Questions? Now, so the user of the lock can take as long as they want. But what about this going to sleep thing? Okay, and how many people have actually stared at the switch code in Nachos? Anybody? Does anybody start looking at the interrupt issues? Okay, a few of you. Okay, there are a few others that are kind of like, what? So let's take a look here. Here's our acquire, and the question is, where do we re-enable interrupts? Because clearly it doesn't make sense to disable interrupts and then go to sleep with interrupts still disabled. Okay, something funny's got to happen. So we might say, well, what if we re-enable here? Okay, why is that a problem? Well, you say we found that the value's busy. Okay, fine. We re-enable here. And meanwhile, at that point, somebody else wakes up, releases the lock, comes back, and we put ourselves on the wait queue even though the lock is free now. Okay, now you got to start getting in the habit of mentally simulating these things, right? So I've got two threads. One of them's got the lock. I'm the guy trying to get the lock. Okay, I can't get it because it's busy. I re-enable. The scheduler takes over this guy, finishes up, frees the lock. I come back over to me and put myself on the wait queue and go to sleep. Okay, that's kind of bad because I'm trying to acquire the lock and the guy just woke me up, in theory. But notice there wasn't anybody on the wait queue, so that's a problem. So what if I put it here? Well, I put myself on the wait queue, and then they free the lock. They wake me up from the wait queue by putting me on the run queue, the ready queue, excuse me, and then I come back here and I immediately go to sleep. So that doesn't work. Okay, what I really want to do is I want to do it there. Somebody tell me what's wrong with that picture. What's challenging about re-enabling there? Right, the thread is sleeping, therefore you're not running any code. Okay? What is this really? Yeah, go ahead. After you.
I was just going to say, like, have your sleep code give it the kernel so to sleep and then read it.
Yeah, exactly. We need to bring the kernel in here to help us a little bit. Okay, it means that our going to sleep process has to also re-enable interrupts somehow. Okay? Atomically together. Okay? Everybody with me on that? All right. We'll talk more about that in a moment. Administrivia. So, as you have started to think about life, the universe, and everything, people are starting to use my office hours. They're Monday, Wednesday, 2:30 to 3:30. So the question is, does that work for people, or are there people here that absolutely can't make those office hours? Okay. If there's a couple of possibilities. One, I could come up with another office hour. That's certainly possible. Or you could send me mail and we could just set up a meeting. Those are always options. So those of you that can't make my office hours, feel free to send me mail and we'll work something out, because I want to make sure that you guys have time to come see me if you need to. And you don't have to come talk about class. I've had terms where people came around and started talking about quantum computing or whatever, or life, or I don't know. So my office hours are there for you guys, so feel free to come by. First design documents due on Monday. And you need to schedule your design review with TAs. Now, hopefully that mechanism's almost up. It is up. Okay, so on the website, you can actually do your sign up. By the way, the design review process timing is between you and your TAs. If it turns out that you can't make it at any of the times or something, you need to talk to your TAs about that. Okay? This is the only design doc due on a Monday. The rest of them are all going to be due on Friday, and so it'll be really easy to schedule the design reviews Monday and Tuesday. That's our normal timing. It just turns out this it might be helpful to a few of you 6 hours before the document's due to get my last lecture on Monday. So I will give you that as an option. Okay? So what's the contents of the design document? Architecture, constraints of correctness, algorithms, pseudocode, testing strategy, test cases. It should be a document, with headers and text, English, not huge blocks of code. You're welcome to use pseudocode, but don't get carried away. So if you have a document that's pseudocode from the beginning to the end, that won't fly. It should be in PDF. Okay, don't send us .text files that are ASCII formatted from, 1972. Send us an actual PDF that looks nice. There's constraints on the website that tells you kind of how many words it's supposed to be and so on. Okay? Questions? Now, one thing I am going to mention, there is a possibility, although it's just become a little less of a possibility, that I won't be here on Monday. In which case, Christos is going to take over and talk to you guys. I think, given the way I'm trying to deal with a fluidly changing thing, which I know I told you originally I was going to be here next Wednesday, and then now it was Monday, which I thought, and now it looks like maybe the thing I have to do will happen on Friday, and I'll be back. But you'll be covered on Monday one way or another. So it's looking like I might actually make it back. Any Administrivia questions? Definitely come on Friday, because your TAs are going to talk about synchronization in more detail than I am today as well. Okay? This is the fun topic of the term, so to speak. Okay. So let's talk about sleep a little bit more here. And if you look in nachos and you look deep in nachos, you'll find that basically interrupts are disabled when you call sleep. And interestingly enough, it's the responsibility of the thread that just wakes up next to re-enable them. Okay? So for instance, let's take a look here. Thread A is running along. It disables interrupts and then goes to sleep. And the sleep code causes the context switch, which actually goes to thread B and then returns from sleep to re-enable interrupts. Okay, and so on. So this is actually the way the interrupt structure is inside of nachos. When you go in to do the switch, interrupts are off. And as soon as somebody comes back from switch, the first thing they do is re-enable interrupts. Okay, so this is kind of how, in fact, we handle that whole sleep thing I showed you with the lock. Okay, because the lock goes to sleep. In fact, the interrupts stay disabled. You go into sleep, you go to somewhere else, it returns from sleep, it re-enables interrupts, executes actual code, and so on. Okay, so this is a self-consistent interrupt system. Okay, if you follow the rules, you'll never find yourself with interrupts disabled but nobody running. Okay, are there any questions? Now what this says is, of course, that you should read the comments in Nachos very carefully. You want to make sure that when you start messing with things in the interior of Nachos, you don't blow something about the things that are supposed to be constants here, like you don't enter sleep with interrupts enabled or something, okay? Or you don't forget to re-enable interrupts when returning from the switch. So these are things you ought to read closely the way the code is to make sure you don't screw it up, because as long as you follow kind of the conventions, and everybody does the conventions, then you get code and a kernel that works. If you don't follow the conventions, then you might end up with a kernel that doesn't work. Okay? Good. Any questions? Okay. So basically, I'm just repeating this. So in Nachos, you'll see lots of comments, assumptions about when interrupts are disabled and when they're not. And just be careful to follow the conventions, or make sure to understand the conventions before you start modifying things, because otherwise you can sort of acquire weird synchronization bugs in the kernel, or weird non-deterministic bugs in the kernel just because you sort of violated some assumption. Here's another interesting thing that's related that I should mention. So you never want to do something like this, right? Here's a case where I acquire a lock, and then I do something that causes a fault of some sort, like divide by 0. Okay, so the issue with this is that now the kernel takes over and grabs, maybe this thread or process or whatever it was, gets killed, and the lock is never released. Okay, so this is a general paradigm of how user code can lock up. You got two things, they're interacting with each other. One of them grabs the lock and then goes off into oblivion somehow. Either they go to sleep, they do an infinite loop, whatever, they execute a divide by 0, and as a result, you never free up the lock. Yes?
Doesn't that imply that locks
Should be what?
operating system managed resources?
Does this imply that locks should be operating system managed resources? Well, it doesn't, for the following reason. The problem with making locks operating system managed resources is that then locking and unlocking is expensive, because you always have to make a system call into the kernel. What it does mean, though, is you've got to be very careful to never acquire a situation like this. Now, if we get there at the end of the lecture, we may have to deal with it next time, but there are languages like Java and C++ and so on that basically have ways of handling non-local exits. Okay, basically situations where you get an exception kind of in the middle of the code, and you can arrange so that no matter what way you exit this code, you always execute release. Okay, and so that's just good programming style inside of C++ or Java or the languages that have these features. You can arrange so that it doesn't matter how bad the code is in the middle, you never exit the code without releasing the lock. I'll mention a little bit about that either at the end of the lecture or next time. Good. Any other questions? All right. So what's the problems with the previous solution? Well, the biggest problem is you can't give a lock to the user. Or excuse me, you can't give an interrupt disable to the user. If you give interrupt disable to the user, then they will lock up the machine. I guarantee it, whether or not it's intentional. And worse or the same badness, you can't actually use interrupts with multiprocessors or multiple threads. So we got to come up with a better lock implementation than what we've had up till now. What we had, by the way, before could work inside a kernel if the resource you're protecting is only running on one node and in one thread, then you could use this. Okay. So what's the alternative? Atomic instruction sequences. Now, remember, for last time, we only had loads and stores were atomic. Instead, now what we're going to do is we're going to have special instructions that do something like read a value from memory and write a new value atomically in a way that can't be interrupted, and it turns out that's enough to build locks. Okay, so this is a case where hardware is responsible for doing the implementation on both uniprocessors and multiprocessors. And then we're going to use some primitives, which aren't going to be quite what we want, to build something more complicated, like a lock or eventually a semaphore or a monitor. Okay, so here's some examples. This is the so-called test and set operation. This one is very common today. Probably every processor you're likely to run into has a test and set. It wasn't always true. But what do I mean by atomic? Well, this is a single instruction, hardware instruction, that basically says grab the value from the address. So that's pull the memory that's at the address, store it in result. Set a 1 to the address and return the result. So what it does is atomically, it grabs the value that was there and stores a 1. And then you look at what you got. You either got a 0 or you got a 1, typically. Okay? Why does that give us a lock? Can anybody figure that out? Yes? Yeah, so the way we do this is we start, oops, that was weird. Hello. No. I think maybe did our system just die on us? Oh, that's a bad sign. Well, why don't we take a break? We are getting close. So any questions so far? How many digits of pi do I know? Well, I knew 200 of them at one point. That's not very many. But that's like just enough to be annoying at parties, but not enough to be truly impressive. Okay. Where were we? Okay, good. So we were talking about read, modify, write operations. It's alive. So we were talking about how this works. So typically a test and set operation, what you do is 0 is unlocked and 1 is locked. And the reason this works, as was being explained before my machine crashed, was that no matter how many people simultaneously try to get a lock, only one of them will be the lucky enough one to catch the 0 and store the 1. Everybody else will get a 1 back. Okay, so it's truly atomic. Even though everybody goes at it simultaneously, only one of them gets the 0 back, and they're the ones that have the lock. Now, how do you release the lock? You write a 0. Okay? Now, there's also swap. This is grab the value that's down there, store the value that you had in a register. That's another atomic one that you can do stuff with. Here's compare and swap. Turns out this one is actually, seems complicated, but it was on the 68,000 processor. And interestingly enough, you can do some pretty cool lock-free queue examples. I'll show you one of these maybe next time if I'm here. And then load, link, store conditional is another example of a type of atomic operation that you can get on processors. This one was on the Alpha and R4000. The point is that these are more complicated operations than just load or store. They're combinations of load and store. And as a result, those combinations are sufficiently sophisticated enough that we can build locks out of them. Okay? So let's look at how we would do this. So this is a flawed solution because it's busy waiting, but here's how we build test and set lock. You guys all caught this earlier. We have a value which is in memory, so this is some lock location. 0 is free. The way we do acquire is in an infinite loop, we say while test and set. Okay, and the only way we exit the while is if we get 0 back, right? Okay, so this thing here is going to be in a very tight loop running test and set until it gets a 0 back, in which case it exits acquire. And the way we do release is we store a 0. Okay? All right. Questions on that? Now this is a solution. It synchronizes, but it's bad because it busy waits. Does everybody catch that? See? While busy, we're busy spinning. So this is an example of a very bad solution that we don't want to have because we're wasting CPU time doing nothing. Okay? And the other problem, and we're going to make a distinction between when wasting time doing nothing and something in a moment here, but notice that the real problem with this is we could be busy waiting a long time, because if you grab the lock and then the user goes off and does some really long operation and then you release the lock, you've just been, somebody else may be spinning for a very long time. Okay? So let's talk about busy waiting. So positives for this particular solution: the machine can receive interrupts. Did you see any interrupt disable in there? No. So there's no interrupt disable there. The user can use this lock because test and set is a user mode instruction. Okay, it works fine on a multiprocessor. Okay, that's kind of cool. So it doesn't matter how many CPUs you've got, you can use this lock across them. Okay, all of the CPUs can coordinate to grab the lock. Negatives: 1, very efficient because of busy waiting. Interestingly enough, the waiting thread may actually take cycles away from the lock holder. Okay, get in that mindset for a moment. I'm busy waiting. Why am I busy waiting? Because I don't have the lock. Well, who's releasing the lock? Well, somebody who's asleep on the ready queue, because I'm running. Okay? That seems bad, right? It means that I'm not giving any cycles to the person that's going to finish up and release the lock. Everybody catch that? This is why busy waiting is a bad thing, okay? And the other interesting thing is priority inversion. If it turns out that the busy waiting thread has higher priority than the thread that's going to release, that holds the lock, game over. Why is that? Can somebody explain to me what the problem is? Yes? The thread that's holding the lock never gets to run. The high priority one's busy computing nothing for a very long time. Priority inversion. You've heard that term probably if you've been working on the project, right? Now, it's amusing to know that the original Mars rover actually had a priority inversion problem. What would happen is the rover would be working along, jump, 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 and then it reboot, just like my laptop just did, right? And it did this over and over again, and they were trying to figure out what's going on. Well, what was going on was there was a data collection thing that was grabbing the bus, all right? And it was trying to grab the bus, and it was waiting on something that was lower priority, that had the bus, and was going to release it. And then there was something else that was actually spinning at slightly higher priority than the thing that had the bus, and it would lock up. Okay, so there's kind of 3 threads. Okay, high priority thing really needed to run, low priority thing had the bus, medium priority thing was spinning. Okay, nobody makes progress. And fortunately, they had been smart enough with the Mars rover to come up with a monitor system that said, oh, no progress being made, better hit the reboot button. So it'd reboot and start over again, okay, and make some more progress before it locked up again. So fortunately, they had thought about this, and actually the rebooting was a positive thing in this instance. But it was a priority inversion issue, okay? And of course, with semaphores and monitors, the thread may wait for an arbitrary length of time, which would be kind of bad if we're spin waiting. All right. So, never put busy waiting into your solutions. Now, does everybody catch the priority inversion issue? You understand what the issue is? The moment you have priorities with threads, if somebody with high priority is waiting on somebody with low priority, you've just negated your priority system, right? Because the high priority one isn't making progress and the low priority one is. Okay. So here's a better lock. How do we get rid of busy waiting? Well, we can't get rid of it entirely, but we can get closer. So here we go. This is going to look awfully familiar, but here's another solution. We have 2 variables now, what we're going to call a guard variable and the actual lock. So remember, lock is blue, guard is red. So acquire does this. It does while test and set. This is busy wait, but only on the guard variable. Then we say, if value busy, put thread on wait queue, go to sleep and set guard to 0 atomically. Otherwise, values busy, guard equals 0, and we exit. So notice that the red portions here are really a test and set lock that's replaced our enable and disable interrupts from our previous solution. Everybody see how this layout is almost identical? Okay. And here's release. Again, we grab the guard lock, we do our thing, and we release the guard lock. Okay, and so the busy waiting in this instance is limited to very infrequent or short, periods of time, because even if you're stuck spinning, the person who's got the lock is going through very fast code and they're going to release it quickly. So this might be the one instance of a busy wait which is kind of okay. But you'd need to justify why you're busy waiting for no more than a short period of time. All right? We good to go? Yeah. You could put a yield in the busy wait. That would be less bad. Because at least you're letting somebody run if they can run. You're still kind of burning up cycles. So it's still not quite elegant, but it's less of a bad busy wait. Okay. Good question. So, and of course, sleep has to be sure to reset the guard variable at the same time you go to sleep. So let's move up a level here. So the goal of the last couple of lectures has really been asking ourselves what the right abstraction is for synchronizing threads. Now, we've been talking about locks, but locks are kind of the lowest level primitive that we could ask for, and they don't really do a lot of things cleanly. Like, for instance, what you're going to see, or what you have been seeing, is locks don't give you a clean way to handle a situation where you have to keep checking over and over again for some condition. They certainly don't give you a way to signal somebody to wake up later, okay, which you really probably want in a lot of circumstances. So we really want good primitives, and we're going to try to move beyond the lock. And the reason we want to have good practices when it comes to synchronization is if you have bad practices with respect to synchronization, you get Heisenbugs and you never figure out what's wrong. Whereas if you program in sort of stylistic fashion that's sort of good practices, you're less likely to have weird, undebuggable bugs. All right, so that's going to be what we're shooting for here. Okay, and Unix, of all the flavors, Linux, et cetera, was pretty stable now, but up until about the mid-'80s, it was basically crashing frequently. And the reason was they had all sorts of weird synchronization bugs in the middle of the kernel that people didn't understand. Okay, so what is synchronization again? It's a way to coordinate multiple concurrent activities that are using shared state. And this lecture and the next is going to give us a way of structuring the sharing portion. And let's talk about semaphores. So semaphores, we kind of have two high-level synchronization techniques, semaphores and monitors. Okay, so semaphores are really named after the notion of kind of the stoplights that are on train tracks, where you see this if you go on BART or whatever. They actually have green and red to say, well, you can go through here or you can't. And Muni has these as well. And of course, when they're ignored by the drivers, then one runs into the other one. And that happens now and then. So a semaphore is like a generalized lock. And it was first defined by Dijkstra in the late 60s. And basically, original Unix used semaphores pretty exclusively. And the definition is a semaphore is a special type of integer. Okay, it has a non-negative integer value and supports the following two operations. P, which is an atomic operation that waits for the semaphore to become positive, then decrements it by 1. Okay, and think of this as wait. And V, which increments the semaphore by 1, and if anybody's waiting on a P operation, it wakes them up. Think of this as signal. Okay? So P and V, those are really descriptive, right? Okay? P, by the way, stands for proberen in Dutch, and V stands for verhogen, okay, which means to test or to increment. So there you go. Very clear what P and V are good for. Okay? Unfortunately, they've been blazoned into the whole semaphore world, so you're gonna have to deal. But P is like a lock entrance point, right? And V is like an exit point. You're going to see this very shortly. And their semaphores are just like integers, except, one, there's no negative values, so maybe they're like whole numbers. Okay? Two, only operations you can do on them are P and V. So you can't read or write the value. You can't look at it. You can only set it initially. So unlike an integer, you can't do a printf with the value or anything. You can never actually find out what its value is once you've set it the first time. And the operations are atomic. So if you do two P operations together, they'll never decrement the value below 0. Okay? Let me say that again. If you do two P operations simultaneously, you'll never get the value below 0 because, say, the value is 1. One of them will decrement it to 0 and get to go through. The other one will stall, waiting for it to come above 0 again. Okay, so they're atomic. Similarly, a thread going to sleep in P won't miss a V. So it won't be the case that you do a P operation, it sees that it's 0, you're about to go to sleep, somebody executes V, and then you go to sleep with the value equal to 1. That will never happen. Okay, so P and V operations are truly atomic with respect to each other. They happen in some order. Okay? Is that clear to everybody? All right, so the semaphore is originally, like I said, from a railway analogy. Here's a semaphore initialized to 2. Okay, so, notice this train went through, did a P operation. Okay, value went from 1 to 2. Ready? Okay, 2. All right, and here went to 0. Okay, so what happens to the next train that executes the P operation? It's got to wait. Okay, now, as soon as the train exits, it executes V that simultaneously increments this to 1. Then the guy waiting wakes up, decrements it to 0 again, and goes on. Okay? Now, semaphores, being integers or whole numbers, have many more states than a lock. I hope I don't have to say that more than once, right? Because a lock has got a 0 and a 1 state, whereas you could have an arbitrary number of integers. So what you should realize is semaphores are already more powerful than locks. That's going to be good, and it's going to be bad. Okay, it turns out if you've got a mechanism that's more powerful, it's possible you can use it in confusing ways. All right, and that's ultimately going to be what we call the downfall of the semaphore. But let's follow it for a moment. So, question? Oh, okay, 2 uses of semaphores. 1, if we set it to 1, which is also called a binary semaphore, suddenly we've got a lock. Right? Because if we set the initial value to 1, semaphore.p is an acquire, and semaphore.v is release. Everybody catch that? Why is that? Because when first one acquires the lock, now the value goes to 0. The next guy tries to acquire the lock, they go to sleep. As soon as I exit, I execute semaphore V, and now suddenly I wake up the guy who was sleeping on P. So this is exactly a lock. Okay? What's the other word that's used for this idea? Mutex. Yeah. Okay? So another thing we can do is we can set the value to 0. Why would we do that? Well, what if you want a thread to just plain wait for something? Okay, think about that. If you only have locks and you got a thread coming along and you want it to wait until somebody else wakes it up, what do? I'm sorry, but that's not in the playbook of a lock. But it is in the playbook of a semaphore set to 0, right? Because I set the semaphore to 0, the thread that I want to sleep does a semaphore.p and it's now sleeping. Somebody else does a semaphore V and voila, it's woken up, it goes forward. Okay? So here's thread join, in a way, not necessarily the way you're doing it. But notice the thread join does a semaphore P, thereby going immediately to sleep, and the thread finish does a semaphore V, which wakes it up. Pretty slick, right? Okay, any question on that example? That's not quite the answer that you were looking for on your problems, but details. So let's go through an interesting example of the producer-consumer with bounded buffer. So here we go. Producer is going to produce things and put them in the buffer. Then the consumer is going to consume things by taking them out of the buffer. Now, what we need is synchronization to coordinate the producer and the consumer. Why? Why do we need synchronization? Yeah.
Otherwise, the producer could fill up the buffer, lose things on there.
So the producer could fill up the buffer. Well, let's assume for a moment that the producer notices when the buffer is full, because that would actually be a single thread problem. But what happens with the producer and consumer working together? Why might that need some sort of synchronization? Yeah.
You don't want them to remove something from the buffer and add something.
Yeah, I mean, think about how you build a buffer. FIFO queue, right? Head, tail, whatever. You go to manipulate the 2 pointers, and both the producer is putting something on and the consumer is removing it, and you end up with a mess. Okay, so the fact that both the producer and the consumer are doing something simultaneously means we got to do something in the middle to control that. Okay, and we don't really want the producer-consumer to, the producer produces everything, then the consumer consumes everything. So we want to basically synchronize access to the buffer in some interesting way. So, if the producer sees that the buffer is full, it wants to wait until somebody starts consuming. If the consumer notices the buffer is empty, you want to wait until somebody starts producing and so on, which is getting close to what you were thinking in a moment ago. Okay? So, Great example, I mentioned this before, the compiler. Here's a case where the C preprocessor is feeding a pipe into the first two phases of the compiler, then the assembler and the loader. And as you can see, each of these pairs of threads probably have some sort of bounded buffer FIFO queue between them, and we need to have some synchronization to make sure that FIFO queue doesn't lose characters or get screwed up. Okay? Coke machine example. All right? Producer can only put in a limited number of cans of Coke, and the consumer can't take cans out of the machine if it's empty. I know there are many of you at late nights would like it to be possible to take Coke out of a machine when it's empty, but I'm afraid that just doesn't work. You may put a lot of money in there, but I'm not sure it works. Okay. So let's see if we can build the Coke machine, for instance, with semaphore. So the correctness constraints here are: consumer must wait for the producer to fill buffers. Okay, right? Because the consumer can't get a can of Coke unless there is some there. Producer must wait for the consumer to empty the buffers. Okay, if the Coke machine is full and the guy comes around and tries to shove other cans of Coke in, you just get a mess on the floor, right? And basically only one thread can manipulate the machine at once, or you really screw it up. Okay, so notice there's actually three separate synchronization constraints. There's a scheduling constraint on not emptying an empty machine and not filling a full machine, and then there's a mutual exclusion constraint on the machine itself. Okay, and remember, the reason we need mutual exclusion is really because computers are stupid. So, in real life, the delivery person's filling the machine, somebody comes up and tries to stick their money into the machine. I guess that would work out, right? You'd figure, the two of them would actually work it out somehow. In a computer, that's not so clear. So that's where our mutual exclusion constraint is going to come into play. And the general rule of thumb with semaphores is you have a separate semaphore for every constraint. So that's why we got three semaphores. One to indicate the buffers, how many full buffers we have, one how many empty buffers we have, and one is a mutex for access to the machine. Okay, is everybody with me on this so far? Well, let's look at some code then. So full buffer initially is going to be equal to 0. So the first value for the semaphore full buffer is 0 because there's no Coke in the machine. Empty buffers is going to be equal to the number of cans in the machine. Okay? And finally, we're going to start the mutex at 1 because we're building a mutex. Okay. So how does the producer look? Producer says empty buffers.p. So first of all, it says wait until there's space in the machine. If empty buffers is 0, there are no empty slots in the machine, and the producer is going to go to sleep right here. Okay, let me say that again. If empty buffers are 0, because there's no, because the machine is full, then the producer is going to go to sleep right here. But assuming that it isn't full, we're going to actually decrement the number of empty buffers. So we're going to say, hey, I'm going to put another can into the machine. Okay? Now, we execute the mutex.p and mutex.v. That basically gives us this critical section so that the enqueue operation is thread safe. So that means this enqueue operation is going to be enqueuing items using, I don't know, whatever you want to come up with, some sort of double linked list, FIFO queue, however you want to implement it. And the reason we put the mutex around it is so that the different threads can't screw up the heads and tails of this buffer. And then, finally, after we're done enqueuing the item, then we say fullbuffers.v, which effectively says, if there's a student sleeping on the floor waiting for Coke, wake him up. Okay? Now, of course, the consumer is the flip side. Consumer says fullbuffer.p. So this is the student. They say, well, if this is 0, I'm going to go to sleep on the floor because I don't have any Coke and can't work anymore. Okay? Assuming that fullbuffer.p has actually been successfully executed, then I know that there is a Coke can there. And so at that point, I'm going to get the critical section in here where I dequeue an item of Coke. And then I'm going to increment the empty buffers because I've taken a Coke can out, and I'll return the item. Okay? Questions? Does this solution make sense to everybody? No questions. You guys are spot on today, huh? Does everybody see why we have 3 different constraints? The mutex is really protecting the shared data. That's this queue. Whatever the queue is, we need the mutex to protect it. The empty buffer and full buffer semaphores are scheduling constraints. They're helping us deal with producer and consumer, so that the producer stops trying to put something on or goes to sleep if the machine is full, and the consumer goes to sleep if the machine is empty. That's handled by these 2 semaphores. Okay? Good. So why is there this asymmetry? Okay, producer does empty buffer.p, full buffer.v. Consumer does full buffer.p, empty buffer.v. So why are we doing this asymmetry here? Yeah. So the producer and consumer want to be woken up for different events. Yes. Continue. Okay. So basically what we're saying here is the producer and consumer are going to sleep and waking up on different events, right? So the producer goes to sleep when there's no space in the machine, and then they wake up somebody as soon as they put a Coke can in. And the consumer goes to sleep on an empty machine, and they wake up the Coke machine man when they've taken a Coke can. Okay? Does it matter the order of the p-values? Okay, let's take a look here. All right? Notice how we've got empty buffer.p, mutex.p, full buffer.p, mutex.p. Okay? Now the answer is yes, I showed you that already, but why does flipping those p-values around cause deadlock? Can anybody explain that to me? Yes? Yeah. So if you have a mutex, suppose we switch these. If we grab the lock and then we end up going to sleep on this guy, which is swapped, then we've effectively gone to sleep with the lock. And therefore, nobody will ever wake up again. Okay? Because nobody will ever be able to dequeue any items to wake us up. Does everybody see that? So this is a situation where the order of the P's really matters. Okay? Because you can deadlock the system. Is the order of the V's important? Yeah.
Yes.
Why?
You don't want to wake up another thread while you still have the mutex. Then they'll go to sleep, and then you'll wake up. You'll return the mutex.
So you're worried about a performance or a correctness problem? So you're worried about a performance problem. Yeah, so the order of the V's doesn't matter from a correctness standpoint. The worst that might happen is you wake somebody up who goes immediately to sleep, who wakes up again. Okay? And in fact, probably that won't even happen that way because you'll just execute the 2 V's in rapid succession, and then, one of them will put somebody on a ready queue and they'll run later. So the V's don't matter. It might affect scheduling efficiency. Yeah. So what if we have 2 producers and 2 consumers? Yeah. So if we have 2 producers and 2 consumers, we have a locking problem. Why is that?
So you need the lock in order to write the buffer, right?
Yep, you need the lock to write the buffer.
So what if two
Well, what if 2 producers go to write the buffer at the same time? What happens? They both try to execute mutex.p. One of them gets it. The other one goes to sleep. The one that gets it updates the queue, releases. Now the other guy wakes up, runs the queue. So in fact, it works. Okay, so this solution works fine even if we have 3 Coke guys and 20 students. Okay? Don't need to change anything. Okay, question? Yeah. Yeah, wouldn't it be nice if there were a double-sided semaphore? There isn't really. So you can kind of see one of the reasons we have two semaphores is we're trying to bound two sides. Yeah, semaphores just aren't defined that way. You're welcome to define one that way if you like. You could come up with a double semi or something, which is probably going to be two semaphores internally of some sort. So semaphores, just to close out in a little bit of preparation for Friday and Monday, semaphores are a huge step up. I mean, imagine trying to do this bounded buffer solution that we just gave you with locks. I challenge you to think about this after class. You're going to see it gets really complicated really fast. Okay? The problem is that semaphores are dual purpose. They're either used for mutexes and they're used for scheduling constraints. And you saw that that little issue of flipping the p's around gave us deadlock. Okay? If you want a type of coding that can potentially deadlock if you accidentally swap things, that might be bad. Okay? And so a cleaner idea is we use locks for mutual exclusion and condition variables for scheduling constraints. So we're going to produce two items to deal with two different things. Okay? And the definition is a monitor is a lock and 0 or more condition variables for managing concurrent access to shared data. Some languages like Java give you monitors natively. Most others give you separate locks and condition variables. If you read the book, it's going to say something like a monitor is a language construct. Okay, don't think that. A monitor is a paradigm for building synchronization. It's a pattern that you should follow. Okay? And basically, a monitor with a condition variable looks kind of like this. Our condition variables each represent queues to have things sleep on it, and the lock is kind of like the entry queue. Okay, so the lock provides mutual exclusion to get in and deal with the condition variables, and the conditional variables are queues of threads waiting inside a critical section. Now, we're not going to talk a lot about this right now because we're almost done, but in contrast to a semaphore, remember in a semaphore you can never go to sleep while you're holding a lock. That was exactly the deadlock we got by swapping the two p's. Condition variables, that's exactly what you do with them. You grab the lock, you check some condition. If the condition ain't right, you go to sleep with the lock. Okay, and then later you release the lock. Okay, it's a stylized way of building synchronization, and condition variables have been designed so that you can go to sleep while holding the lock. Okay, make sure you hear that, because it's a little different from what we talked about with semaphores, where that was right out. Okay, so here's a simple infinite queue, which I'm going to leave you with. But notice, this is a lock acquire, queue.enqueue, lock release. Okay? And notice that this just looks like a lock. Why is that? It's a monitor with 0 condition variables. Not very interesting, right? Okay? But let's add a little bit of an interesting constraint. Like suppose when we go to remove a value from the queue, you want to go to sleep if there's nothing there. Well, now we have a full monitor. Say, take a look here. To add to the queue, we acquire the lock, we enqueue the item, we signal the person who might be sleeping, and then we release the lock. On the remove from queue, we acquire the lock. In a continuous loop, we say while queue is empty, sleep, data ready.wait. And we're going to keep looping, because every now and then somebody will signal us, we'll wake up, we'll check the condition again. If we're not empty anymore, we'll exit, we'll dequeue the item, we'll release the lock, and we'll return. Okay, so this is a very good single condition variable pattern for you guys to think about. Okay, and we'll talk more about this in section on Friday and more about this on Monday. But notice this idea that only one item is ever actually looking at the state at any one time. So either we're acquire release here or acquire release there. And notice how we go to sleep with the lock acquired. We wake up, and we think about this as when we wake up, we have the lock still. Okay, so we say, is the queue empty? Yeah, go to sleep. we wake up later, we have the lock. That's the way to think about this, because the way you look at that code is lock acquire, lock release. Okay? Good. Now I should quit because we're over time, but are there any questions on this? Brief questions? Okay, so in conclusion, we talked about atomic operations, which is an operation that runs to completion or not at all. We talked about hardware atomicity primitives like test and set or swap, disabling of interrupts. We showed several ways to build locks. We talked about semaphores, and we started talking about monitors and condition variables. In class on Friday, they'll talk a lot more about monitors, and on Monday, we'll nail it with the read-writer example. So have a great weekend, and I may see you on Monday.